Support vector machine regression. So SVM regression is going to adapt the ideas that we've used for classification into regression. And that idea is mainly around taking some sort of prediction tube with curves again. So here we have a curve, and here we have a curve. And this is going to be our prediction tube. And the general idea is, unlike classification, where we're trying to get our support vectors to be on the outside, on the inside of the curves, right? So we classify things on the outside of the curves. With regression, we're going to inverse that. So instead of our support vectors trying to be on the inside of the curves, our support vectors are going to be on the outside of the curves. And that will give us a capability to actually build a regression model here, which is our linear line. Using support vector machines. So when we look at something like this image here, which is linear support vector regression, the presence of additional training within the margin does not influence the prediction of the model, right? So we can also call that as epsilon insensitive. Now, what does that mean? That means if I take a blue dot and I add a blue dot here, and I add a blue dot here, and I add a blue dot here, it does not change the regression of the model, right? The only thing that changes the regression of the model is if I were to add a blue dot here on the outside, which then becomes a support vector. So if you've ever trained a support vector regression model, right, you might notice that it, along with many other models, but it is somewhat sensitive to data, and that data depends on if it's on the inside or the outside, right? So it's very sensitive to data on the outside of your curves and non-sensitive to data on the inside of your curves. So you can use that to your advantage by setting a margin. And again, we're going to set our margin with our parameter epsilon. And that will help us set our margin here. So here we have a very wide epsilon, and then here we have a somewhat narrow epsilon of 0.5, and here we have a wide epsilon of 1.5. So that's kind of the general idea of support vector machine regression, is we are trying to keep it inside. We're trying to keep the support vectors on the outside and classify the data on the inside. Whereas with support vector machine classification, we were trying to keep the data on the outside and support it with the support vectors on the inside of the curves. sklearn makes relatively simple work of support vector machines. So it's linear SVR for support vector machines. We can also do non-linear support vector machine regression. And again, to do nonlinear support vector machine regression, we're going to have to use the kernel trick. And the kernel trick is going to warp our space up and down around the, let me put my, oh, I just need to move it. The kernel trick is going to warp our space up and down around, going to warp our space around our data, right? So to build the kernel trick, we need to look at a nonlinear relationship, and we can build out our cost function with the kernel trick as follows. F of x is equal to the summation of our instances from 1 to however many we have m for alpha of I minus alpha of I starred k, which helps us with our, which gives us our kernel, and we'll input into our kernel, whatever our kernel may be, x of our given instance and all of our data x, and that's what's going to do the transformation plus b, right? And so this is our kernel. Now there's several different kernels that we can use, RBF or polynomial, and probably either of them can be are commonly used, and you can get to either of them in sklearn. But let's go ahead and look at an example of nonlinear regression using SVR in a kernel, right? So here we are with nonlinear regression using SVR in a kernel. This is a second degree polynomial kernel. That's going to allow us to warp our data so then we can do the support vector machine regression and then warp it back so we can get something that looks like non-linear, non-straight lines. And the SVR class supports a kernel trick and actively kind of helps to capture these. Again, we're going to have some parameters that we tune here. Here I've got C equal to 100,000, so I can make it really strict. That's going to try to force as much data to the outside as possible, and you'll see that I get a curve that kind of looks like a very high smiley face, I guess. Now, if I release my regularization factor C, I can get a much lower curve, which definitely kind of cuts through the data differently. To me, at least, it looks like I perform worse over here with a lower regularization, but I'm actually pretty good over here. Here I perform quite well over here, but over here on the left-hand side, it might not be as a little bit overfit, right? But it's at its core, it's just a polynomial data set with noise, but it's always interesting to see kind of what the regularization terms mean. And again, C is a user set parameter.